guess that's what I'm going to do if people don't have questions, and then we'll kind of revisit some of it. But like we're not going to do any of this stuff for a week. Um, but we're still talking about, we just recently started talking about particle kinetics. We defined mass. We're in the middle of defining force, and we'll we'll eventually see how to use that stuff in Newton's second law. I mean, I guess I'll sort of start with examples as we go through different force types. But if anybody has any homework questions or anything, I'd be happy to spend as much time as you want on that. Yeah. Yeah. Yes. So yeah, let's tell me if this is the kind of problem you're talking about. I'll just like make something up. So, um, okay. So, um, so let's say that this has a radius of 0.2 meters and an angular velocity. Let's call this point C in the middle. I'll come back to that later. And let's say we have an angular velocity this way of 10 radians per second and an angular acceleration this way of 20 radians per second squared. And let's say we want to figure out what's happening at this point over here, P. And let's do it two ways. One, assuming that that hinge at C is fixed. So what are the velocity of P and the acceleration of P if C is fixed? And second, what are the velocity of P and acceleration of P if um, so let's say that that point C now, so now this thing is like mounted to some kind of vehicle and the vehicle's driving around. And so now we still have these angular motions, but now there's a velocity of C that's equal to 5, 10 meters per second. And there's an acceleration of C that's equal to negative 20, 15 meters per second squared. Does that get it? Oh, part B would be relative motion. That's right. Oh, oh, okay. Oh, all right. Yes. So we're not doing this. Um, well, it says so. I think the problem says something like, say that the angular velocity is clockwise with some value, and say that it's slowing down with an angular acceleration magnitude of something. And then it asks for the angular velocity and angular acceleration vectors. Okay. Um, well, that wording just comes from, like, I took part of that problem from a question like in a different class. And so we haven't talked about these as vectors. Okay, but what those vectors, so for us, and so really just the answer is if it's going clockwise at 10 radians per second, then that's an angular velocity of negative 10 radians per second because the clockwise puts that negative sign on it. Okay, so that's all it is when I ask for the angular velocity and angular acceleration vectors. I'm just asking you to put the signs on it. Exactly. Yep, that's all. Um, while we're on this, and I should erase that vector word because it's confusing because I haven't talked about it as vector. But angular velocity and angular acceleration are vectors. And meaning of, so you can think of these things happen in 3 dimensions. And at any instant, something that's rotating has a instantaneous plane that it's moving in. So something that's moving all around, if you track its angular motion, just at that instant and the instant a millisecond before and a millisecond after, makes a plane, defines a plane, and it's in circular motion in that plane. And the angular velocity vector, the direction of that vector, it's the right-hand rule. Maybe you've seen that in math here and there, maybe before, maybe not. But it means the vector is the direction of your thumb when your fingers do the rotation that fingers can do. Unless you're double jointed, then it's confusing. But the way standard human fingers work, So in this case, if the angular velocity is this way, to define that as a vector, you put your fingers in the direction of the rotation, and your thumb says the angular velocity vector. If we call this x, this y, then z would be out. So you'd have an angular velocity vector of -10 radians in the z component. So we're not gonna do that. But like when you go on to dynamics and stuff later on, the people who are doing engineering, that'll all be done that way.
Could you do number 2 because I try to find the vector velocity on, for example, trying to find that, and I got, for example, top relative to the ground is 0, 0. Can you show the problem?
Sure.
First?
Anybody have that? I don't have that one in front of me. This is the same one, number 2.
Yeah.
Thank you. Okay, so the child is on a carousel. These things I'm talking about, actually they seem to be not put on playgrounds anymore, because I have found anecdotally that every single kid who rides one gets injured. But it's he is. He has a toupee too. But it's these circular plates that someone grabs onto the thing and spins it around, and then the kid. Well, so what's going on is then the kid's in circular motion, and in order for that kid to stay in circular motion, he has to accelerate a lot, and to accelerate a lot requires forces, so he feels the acceleration, and if his butt friction can't apply enough force to keep him accelerating in that way, he flies off. So from above, let's say this is the top of the kid's head. And it's moving counterclockwise from above with an angular speed of 2.5 radians per second.
I have a question.
Yeah.
Could that, for example, that a person could be in the left side of it instead of the bottom side? Because it sounds like it's the same problem.
Yep. Yep. You can put it anywhere, and you can even, if you want to try to figure out for yourself how to do it, it's not too complicated. Try one of these problems, putting the object over here or something.
Okay.
You just have to do the trigonometry to figure out the directions of the velocities and accelerations.
So on the test, do you matter where we put on each of the direction? It don't matter, right? It doesn't matter. For example, for example, put it on the left of the center.
Yeah, if I don't specify, then you can put it anywhere. Okay. Probably on tests, I'll always specify because I want answers to look the same. It's easier to grade. But yeah, if I don't specify, you can put it anywhere. So there's the angular velocity. And then the slowing down, which means the angular acceleration has to be the opposite direction. And it has a magnitude of 9.5 radians per second squared. And says to draw a picture from above. And now we're going to do the thing like we've been doing in lab over and over again, where so this is the path. Because of the direction of the angular velocity, we know that the velocity vector is this way. Because angular velocity and angular acceleration are opposite directions, the tangential acceleration is this way. Centripetal is always towards the center. And so the total acceleration is somewhere in that range. So that's part A. And then part B, omega has a magnitude of 2.5. Since it's counterclockwise, that's positive. So positive 2.5 radians per second. Alpha has a magnitude of 9.5, and it's in the clockwise direction, so negative 9.5 radians per second squared. Velocity vector. So now we already have everything we need to figure out the directions, but we need to calculate the magnitudes of these vectors. So the velocity vector, the speed, is equal to the angular velocity magnitude times the distance from the center of the circle to the point. Question? Yeah, the vectors are in there. That's a typo. I should change that. But so all you have to do is give the values of the angular velocity and angular acceleration, and that means anything counterclockwise is positive, and clockwise is negative. But you know what I was saying before is they really are vectors. There's no reason really for us to think about it that way yet. But the meaning of that is curl your fingers in the direction of the angular quantity. Your thumb goes in the direction of the vector. So the angular velocity vector, since the angular velocity is like this, your thumb is this way, so that would be 0, 0, 2.5. Okay, you know, in the z direction. And this one, since the angular acceleration is that way, your thumb is that way, so this would be 0, 0, negative 9.5. So that's the meaning of vectors, but you don't have to worry about that yet. Later on, that's how you'll do it. Okay, so the speed is the angular velocity at 2.5 times the distance from the center of the circular motion to the point you care about. So that's 2. And so you get a speed of 5 meters per second. And now combine this, you know, we know it's this direction. We know it has a magnitude of 5. And so that's in the positive x direction, 5 meters per second. So 5, 0. That's the velocity vector. Yes.
If trying to find the velocity of C vector, would it be that vector? Velocity
of C?
Yeah.
That point C, you know, just so this is a thing that the center is mounted to a pole that's mounted to the ground. So that C isn't doing anything. You know, it's part of the ground. You know what I mean? Carousel is rotating around that point. So the the velocity and the acceleration of that point C are 0. That would be different if this was mounted on the back of a truck and the truck was accelerating while this stuff was happening. Then you would use relative motion, like that problem that I wrote up above but didn't do. Okay, now we want to calculate the acceleration. And we know that the magnitude of the tangential acceleration is alpha times r. And so that's a loud movie. 9.5 times 2 is 19 meters per second squared. And now combine this magnitude with the direction that we figured out in part A. And so the tangential acceleration is negative 19.00 meters per second squared. Well, what these formulas let you calculate is the magnitude of those vectors. Okay, vectors have two things. They have directions and magnitudes. The formulas let you calculate the magnitudes, and that's why it's absolute value. So there are two things with vectors that seem kind of related. They're not exactly the same. One is magnitude. Magnitude is always positive. And the other one is multiplying a number by a vector by a number. That can be positive or negative. Okay. In this case, we're calculating the magnitude. And so we're just figuring out how big it is. It's always positive. And then we're combining that information with the direction that we know from like inspection, like we did in part A. Okay, so that's the tangential acceleration vector. And now the centripetal, the magnitude of that is omega squared r. And because of the square, we don't have to worry about an absolute value. And so this is 2.5 squared times 2. And so that's 12.5 meters per second squared. Now, what we know about the direction is that it's in the positive I direction. You know, I didn't draw a coordinate system, but if you use the one that most people would choose, the centripetal acceleration's in the positive y direction. So if you combine the magnitude of 12.5 with the direction positive y, you get 0, positive 12.5. And then finally, the total acceleration, which is what it asks for, is the tangential plus the centripetal. So that's negative 19.00 plus 0, 12.5. You get negative 19.0, positive 12.5, adding and taking away significant figures at will. And then meters per second squared. Okay, so what quadrant is that in? Second quadrant. So now we can go back and make sure that that makes sense with our analysis before. And yeah, that's exactly what we do. Somewhere in the second quadrant. So our numeric and our sort of intuitive ways of thinking about this agree with each other. Any questions about that one? Any other homework questions? Yes. Yes. Yes, that's right. Okay. Mm-hmm. Okay. Yeah, let me go through number 4. Okay, so we're talking about a golf cart, but all that we care about is the wheel part of the golf cart. Um, and the wheels rotate counterclockwise and accelerate clockwise. So the angular velocity is like this, um, and it has a magnitude of 8 radians per second. And they accelerate clockwise at 12 radians per second. So is the golf cart speeding up or slowing down? Slowing down, yep. And the radius of the wheel is 0.15 meters. Um, okay, and then it's going to, all this one asks for is the velocity and it asks for some directions of motion, just picturing what's happening, if it's speeding up or slowing down, and then calculate the velocity vector and the acceleration vector of the golf cart. All right, well, which direction is it moving at this instant? Which way is forward? Right. Yeah, it's moving to the, wait, no, it's moving to the left. Yeah. Yep. Okay. Question? Or sort of related to that? The direction it's moving is dependent on the angular velocity. It's like when you, just like if you have an acceleration and a velocity of an object, translational velocity and acceleration of an object, the direction it's moving at that instant is the velocity. Oh, thank you. This one should be squared. Yeah. That wouldn't make any sense to have two angular velocities. So at this instant, the angular velocity is this way, and that's related to the direction it's moving. And this one is just saying it's opposite of that, so it's slowing down. Okay. So the direction of motion comes from this, and all you have to do is just picture if it's rolling like this, it has to be moving that way. Okay.
Doesn't it mean like within less than a second it will start moving that way with the acceleration?
You'd have to do the calculation to figure out how long it would be. I guess you're right, in less than a second, yeah. Yes, if that acceleration keeps up. But something important to keep in mind is when we look at a picture like this is telling us what's happening at a single instant. It doesn't give us any guarantee that it's going to do that in the next instant or it was doing it in the instant before. So as far as we know, it just, a snail pushed on it or whatever, just this instant. And then it's going to mash the snail and then keep going, you know what I mean? So a figure like this is instant by instant. The only way you'd know more about it is if you get this stuff as functions of time, or if it says constant. Okay, so we know that it's moving, the velocity is this way. And we know that the velocity of the center, or we know that the speed of the center is equal to omega r. And that's the same formula as for calculating the velocity of points that are rotating around a center. And they're not unrelated to each other, but you need to keep in mind that those are different formulas. We're not using the formula here for the velocity of a point moving around the center. That is specifically the formula for rolling without slipping, and that's the velocity of the center. Okay, so those concepts need to be different in your mind. Okay, this is rolling without slipping. And so put those together. Well, we're just looking for a speed, so that's absolute value. Put these together, you have 8 times 0.15. So that is 1.2. And now to come up with a velocity vector, we see from this picture, from just inspection, we could tell that that's moving in the negative x direction. We're using this one. And so the velocity is negative 1.20. And then the acceleration vector, the rolling without slipping equation, says that this is equal to the absolute value of alpha r. And so this is equal to 12 times 1.5. And so that's 1.8 meters per second squared. And how do we know the direction of the acceleration of the center? What? Anybody? We know that it's slowing down. That's exactly it. Yep. And we know that the center of the wheel just moves parallel to the surface. So that's just going to be this. And so the acceleration of the center, not absolute value, is positive 1.80. And if it asks you something about velocities or accelerations of points on the outside of the wheel, now you'd use that as the acceleration of the center relative to the ground and use relative motion to figure out the acceleration of some point P relative to the ground. Any other questions about that one? Anybody want to do 5? Anyone?
Can you illustrate like the acceleration of like the center relative to the ground? Can you illustrate like
For number 5?
No, for number 4 to say.
Yeah, sure. Okay, so what if we wanted to calculate, let's say we wanted to calculate the acceleration of this point. We haven't done that before, I don't think. So what's the acceleration at P? Well, we're going to use relative motion equation that says the acceleration of P relative to the ground is equal to the acceleration of P relative to the center plus the acceleration of the center relative to the ground. And this one is what we just calculated. And this one is circular motion. Okay, so to calculate the acceleration of P relative to the center, that's a tangential acceleration plus a centripetal acceleration. And the meaning of, the fact that we're calculating the acceleration of this point P relative to the center is saying, now imagine that the center is fixed. What are these, what's the acceleration of this point in that case? Okay. So we still have all the same angular motion, but now we're saying the camera that we're using to measure the motion is moving along with C. So it doesn't see that point C is moving. Okay. Okay, well, we know that we have an angular velocity this way of 8 radians per second. And we know we have an angular acceleration the other way of 12 radians per second. So the first thing we need to do is figure out the directions of the tangential and centripetal acceleration vectors. So the velocity based on the angular velocity is this way. It's slowing down, so the tangential acceleration is this way. Centripetal is always towards the center. So the total acceleration when we calculate it is going to be somewhere in here in the third quadrant. Okay, so we just have to calculate tangential and centripetal separately and add them together. So the magnitude of the tangential acceleration is alpha r, and that's 12 times 0.15. And that is 1.8. And from inspection, we know that the direction is in the negative y direction. So the tangential acceleration vector is 0, negative 1.8. And then the magnitude of the centripetal acceleration is omega squared r. And that's 8 squared times 0.15. So 96, 9.6. And from the directions that we figured out before, we know that's in the negative x direction. So centripetal acceleration vector is negative 9.60. And, in these problems with a lot of steps, one of the hard things is just keeping track of where you are in the whole process. Like we calculated this, like, what are we even doing? Well, remember that what we're doing here is we're calculating the acceleration of P relative to C. So we need to add these two together to get the acceleration of P relative to C, as if the center was fixed. So the acceleration of P relative to C is 0, negative 1.8 plus negative 9.60. And that's negative 9.6, negative 1.8 meters per second squared. And now we can go back to the relative motion equations. The acceleration of P relative to the ground, that's what we're looking for, is equal to the acceleration of P relative to the center plus the acceleration of the center relative to the ground. Acceleration of P relative to C is what we just got.
Acceleration of c relative to the ground is what we had earlier, 1.80. And so you get a total acceleration of negative 7.8 and then negative 1.8. Okay. And so that is, compared to the ground, that's the acceleration of that point P. And what we're just starting to get into with, so this is still kinematics, this problem, but what we're starting to get into with kinetics says this idea of calculating acceleration relative to an inertial coordinate system, which you can think of as the acceleration relative to the ground, is really important. To use Newton's laws, you want to calculate the acceleration of the point relative to the ground. Well, I keep saying the ground. The ground is also accelerating, you know, because we're on a planet that's hurtling through space and whatever. But it's accelerating very little, because if you think about so the Earth goes through one rotation every 24 hours, you know, so 2 pi every 24 hours. Divide that out and you get a really, really small angular velocity. And that corresponds to a low acceleration at the surface of the Earth. So for almost any practical purpose, we assume that the ground has no acceleration, and we can use that in Newton's laws. There are counterexamples, but you need to want extremely high precision for the ground not to work as in like Newton's laws. But if you need ultra high precision, then you also need to take into account the fact that the Earth is rotating. What would be the use of calculating the acceleration of this point P relative to the ground? If it's on a wheel that's rotating, well, I like bikes and stuff, so this is the one that occurs to me, is if you're trying to figure out, so people like their bikes to be, you know, about as light as they can and still work well. So if you're designing a fender for a wheel and you want to put as little material in that fender as you can and still have it block mud that's coming up, remember that Newton's second law says big accelerations correspond with big net forces, okay? And that's true of particles of mud that are stuck to your wheel too. And so if you analyze the accelerations of all the points on the wheel, you know, in a usual application, and you find the places where there's a big acceleration, those are the places where the mud needs an extra big force to stay on the wheel. That sort of makes sense, right? And those are the places where the most mud is going to fly off. And so, you know, you calculate, okay, over here, I need this, you know, maybe you could cut down the fender to only be this big, but just in a specific spot or something. I don't know if that would work. Probably not, or someone would have done it. But that's the kind of thing that you could use that idea for. So I say that because this all seems pretty abstract, but we're already getting into stuff that can have, you know, really useful engineering applications. Any other questions about that problem? Okay, let's stop, and I guess we'll just go back into forces after spring break. We do have lab tomorrow, and man, I think I'm going to do everything I can to get your binders back to you in lab tomorrow, and I really think I'm going to. Yeah.
F basically find the